Hello everyone, and welcome to this week's SMaRT seminar series. It's my pleasure to welcome Dr. Emma Lejeune. She is an assistant professor in the Department of Mechanical Engineering at Boston University. She earned her PhD from Stanford University in September 2018 and subsequently held a Peter O'Donnell Jr. Postdoctoral Fellowship at the Oden Institute for Computational Engineering and Sciences at the University of Texas at Austin. She joined Boston University as a faculty in 2020, and her research currently focuses on combining data-driven and physics-based computational modeling approaches to characterize and predict the mechanical behavior of heterogeneous materials and biological systems. Now, with that brief introduction, please join me in welcoming Dr. Emma Lejeune for the presentation today. And Emma, it's all yours.
All right. Thank you so much for the introduction and for inviting me to come share my work with all of you. I'm excited to get to talk about some of what my group has been working on. So just very brief introduction. My name is Emma Lejeune, and I've been an assistant professor at Boston University since 2020. This right here is a photo of the students in my group. We have Hiba, Jeffrey, Saeed, Kwan, Irfan, Sarah, and Lingzhao. All of them contributed in various ways to the work that I'm going to present today, especially sort of always discussing kind of the big picture ideas that I'm going to talk about. But Saeed and Irfan's work in particular is going to be highlighted in this talk. Okay, so my group works on a bunch of different topics. We do a lot of work in computational methods development, and we work on applications in mechanics, biomechanics, mechanobiology, data science, scientific infrastructure. And sort of the thing that combines all of these disparate areas is really trying to think a lot about the question that I have on this slide. So central sort of scientific question in our work is basically, how do we know when a method is effective, generalizable, and reproducible? And this is something that we care about when we're thinking about problems in, for example, scientific machine learning. Say we want to apply a machine learning technique to a problem in mechanics. There's so many different methods available. How do we choose the best one? And if we develop a novel method, how do we show that it's useful or that it outperforms what else is available? And then the other thing that we spend a lot of time thinking about is essentially working with collaborators in biomedical engineering. And in that case, it's an entirely different application space, but still this question is relevant. So the slides right here shows a problem we're working on with CellMet, an engineering research center here at BU. And our collaborators over in biomedical engineering work on this very cool technology where basically they have ways to take cells very minimally invasively from patients, so think like skin or blood samples, reprogram those into stem cells, then differentiate those into cardiomyocytes that can be then used for things like patient-specific drug discovery, disease modeling, or tissue engineering. But there are all sorts of problems with these protocols along the way. There are all sorts of subtle changes that you can make. And if you're really trying to come up with something where you're going to do some form of quality control or really try to get it into patients or the clinic, it's really important to sort of have the methods locked down. And just like the scientific machine learning problem, figuring out what the best method is or showing that a new method is useful or better than what else is out there is really not necessarily straightforward. So we spend a lot of time thinking about this general question, and I think the answer to it is really kind of multifaceted. On this slide, I have the statement, we need benchmark data sets, performance metrics, and validation studies to advance methods that rise to the current moment in methods development. So big data, machine learning. And these sort of three areas, kind of developing benchmark data sets, defining performance metrics, and conducting validation studies are maybe sort of like the broad strokes of what I want to talk about today. And in this talk, I'm basically going to give like a little snapshot from three different areas of our work. First, some work on developing benchmark data sets, then some work on thinking about performance metrics for problems in tissue engineering, and then finally, some very recent kind of work that we've been just getting started on and developing validation studies and benchmarks to assess the performance of large language models and writing finite element analysis code. So I've been through kind of the high-level motivation for what I want to talk about. And now I'm basically just going to jump in to each one of these three snapshots. And I think some data said questions mostly at the end, but if there's anything that you want to just clarify quickly on any of these slides, don't hesitate to interrupt because I want to make sure that people are able to follow along. Okay, so benchmark data sets, that's the first thing I want to talk about. So what's the motivation for developing benchmark data sets? There are all these different challenges that we're facing in the scientific machine learning research space, right? It's hard to compare different methods. Claims often can't necessarily be tested. Sometimes models don't generalize well. It can be hard to reproduce other people's findings. And just sort of looking out at the world, especially in sort of different disciplines that are relying heavily on machine learning, we really think that thoughtfully designed benchmarks could help sort of improve this and make our claims testable, our methods comparable, and our results also more reproducible. And we've been working on this problem for, I guess, a little over 5 years at this point. In 2020, this slide I made in 2020. So when we started working on this problem in 2020, the research space felt very focused on kind of meta models, especially meta models of heterogeneous materials. You can see all these references are from just before 2020 or about 2020. And basically, this idea of creating meta models or models of models is really powerful when you think about the applications listed on this slide, right? If you want to perform multi-scale modeling, material design optimization, uncertainty quantification, sensitivity analysis, real-time prediction, data integration, really anything where having a really high number of simulations can let you perform breakthroughs, this becomes a very powerful concept. So around 2020, there was a lot of literature being published in this space. And similar to the way that I opened my talk, the thing that was kind of bothering me at the time, or that I was thinking about a lot, is that there really wasn't a clear picture of what types or architectures of metamodels are best for engineering mechanics data, right? So this slide has, 3 different examples, but, this is 3 out of hundreds of potential options that you could choose from. And just like I was saying before, this is really problematic if you're somebody who is, say, like methods agnostic, doesn't really care what method you want to, what method to use. You just want to solve a scientific challenge. It's hard to sort of look over and see which method to pick up. And it's also problematic if you're developing new methods and want to say like, hey, my method's the best and here's proof, right? So this sort of was on our minds. And in 2020, we were kind of looking over at the computer vision research community and seeing what they were working on. And it kind of occurred to us that it would be nice to have some similar data sets for the mechanics research community. So this is a very old and popular data set. It's very simple, right, from the computer vision research community. The MNIST data set, where the goal is to basically predict what digit, kind of a collection of handwritten digits that are 28 by 28 bitmaps actually is. And what we did is we took all of those bitmap patterns and we turned them into finite element analysis simulations with a stiff inclusion and a soft background matrix. And we applied some deformation, and we were basically able to use that to sort of develop just a very basic benchmark. And we like this because it's useful both sort of to serve as like a direct reference to something that's relatively well known, but also the MNIST data set is a really convenient size, and it borrows that directly from it, right? This data set is one that you can download on your computer in a couple minutes. It's relatively painless, but it's also big enough that you can actually meaningfully train neural networks with it. And our thoughts here were that this would be sort of a drop-in mechanics relevant replacement for the original MNIST data set, which a lot of sort of algorithms and tutorials are demonstrated on. So here's our initial data set from 2020. And from 2020 to 2023, we did a lot with kind of expanding that initial idea. So we had a bunch of different load cases. So we thought about different kind of baseline models. We added the fashion MNIST data set, so thinking about sort of this like more challenging parameter space. These are basically like photos of different articles of clothing, and it's a bit more diverse than what you have with the digits. We thought about different simulation fidelities. In this case, we published a short paper on transfer learning in this case to allow kind of like a multi-fidelity modeling situation. And then we also made a version of the data set that is suitable for basically full field prediction with mechanical nonlinearity or with material nonlinearity in it, where we have this kind of phase field fracture example right here. So that's what we were working on from 2020 to 2023. And we're kind of getting excited about benchmarks, but then we sort of wanted to take a step back and really work on something that would sort of ask more questions kind of the broader mechanics community. And basically since 2023, we've been pretty focused on developing some more sophisticated benchmarks like the one shown on this slide. And I'll say also that SMData has a really nice benchmark that is pretty similar to this. And I think maybe some aspirations of working together on that, which is something I definitely look forward to in the future. So basically, the idea behind this work is essentially that predicting fracture behavior is a computational mechanics grand challenge, right? If you go to a computational mechanics conference right now, like for example, my group went to a computational mechanics over the summer. There's a bunch of different sessions that will be running on phase field modeling, and there are all sorts of controversies within the phase fields modeling kind of research community. But one thing that I think everybody can kind of agree on is that this technique can be very computationally expensive, especially if you're looking at more complex domains or thinking about moving towards 3D. And in those scenarios, right, you can see a very clear motivation for wanting to introduce some machine learning or kind of machine learning based approaches. So what we've done for this initial benchmark data set is that we've initiated 1,000 crack patterns, tension and shear boundary conditions, and then we've used 3 different energy decompositions. So basically we have spectral, volumetric, deviatoric, and star convex energy decompositions for a total of 6,000 simulations that make up this benchmark. And we ended up including these different energy decompositions because we found that in shear, they would actually not always, but sometimes lead to different results. It's a little bit hard to see on this slide, but if you just focus on this column under the shear heading, you can see basically across these different energy decompositions, you often end up with different, sometimes very different, sometimes more subtly different crack patterns. And we wanted to have a data set that kind of highlighted that complexity, both so that it could be used to look at the performance of different machine learning models in a relatively simple way, but also so it could motivate development of methods that would perhaps maybe leverage or extract more meaning from computational methods that have some kind of spread or uncertainty in them, like this. And I'll just say that there has been a handful of work by others on implementing machine learning models for phase field fracture, solving phase field fracture problems. One thing that we sort of tended to see in the literature is that there has been a lot of sort of validation on simpler problems. There's also been some work looking at kind of more complex domains, but we felt that sort of basically, like, even though there are a lot of promising techniques out there that are able to perform well, we really wanted to be able to kind of develop a benchmark that would sort of push these techniques and maybe break them and highlight where there needs to be additional work. So here's an example of some of the prior literature on these phase field fracture data sets, or sort of predicting phase field fracture outcomes with machine learning approaches. We haven't evaluated all of these methods on our data set, but we think that this would be potentially a really interesting area for future work. So just sort of as kind of like a baseline, so sort of running some different machine learning models on our data set as a starting point, we implemented a pin architecture that was published super recently, 2024, that was specific to phase field fracture. And if you look at kind of these initial conditions and what the finite element analysis ground truth is supposed to look like, you can see that sort of implementing the physics-informed neural network framework that was designed specifically for fracture problems didn't necessarily lead to solid predictions. And we're very open to the idea that someone with more experience training these models could create a implementation that does better. But so far, what we've seen is that though it looks like these physics-informed neural networks are sort of getting somewhere, there is definitely a need for more development in this area if you want to try to predict fracture patterns, these more complex fracture patterns. We also have some fairly similar results for Fourier neural operators. The Fourier neural operators are trained on the data, and they ultimately do okay. But we sort of felt that the results that we were able to develop still highlight a need for future work, and I'll sort of talk about that on the next couple of slides. So this plot right here shows basically a force versus displacement curve, and it shows the average and then the plus or minus 1 standard deviation across all of the 1,000 examples in our data set. And you can see if you just look at the data itself without thinking about any of the machine learning models trained on it, that when you're in this initial elastic regime, the standard deviation is pretty small. Behavior across all samples is relatively consistent. But then when you get to sort of this initiation and propagation regime where the actual material nonlinearity is occurring, you have a much larger spread in your data. And you can imagine that from a machine learning perspective, that would be much harder to predict. And that's what we see when we look at the data, right? So in these plots right here, we have an error metric on the y-axis, and then we're basically showing step number on the x-axis. So up here, we have our phase field damage fields, where this red curve that maps basically to the left shows the mean squared error. And then this right curve that corresponds to the right axis maps the dice score, where basically 1 is perfect prediction, and the predictions look really good at the beginning. But then basically as you get farther and farther into the process, the error increases a lot, reflected by a lower dice score. And similarly, if you look at the mean squared error in the x displacement and y displacement fields, you can see it starts out very low and then increases as these simulations progress, right? We can also look at the Fourier neural operator error like this. So this is basically the performance on the predicting the damage fields at the last step. We have 5 different seeds that we trained, and you can see basically the spread and an F1 score. So with an average F1 score overall, somewhere this like 0.62-ish value. And here we basically have an illustrative kind of worst case scenario prediction where red is the ground truth, and then the gray is the superimposed prediction for all 5 seeds. And here's sort of a best case scenario where, again, red is ground truth and gray is the superimposed prediction for all seeds. And you can see that, in some cases, these models work really well. But at least in my opinion, there's a lot of room for improvement here and developing kind of better, more performant models, especially because in engineering applications, we really want things to be like 100% correct, right? And I think that's one of the things that maybe separates some engineering applications from other work out there. So we've been working on benchmarks for the past 5-ish years. And one thing that we've really grown to appreciate is that sort of community engagement on this topic is super important. I think the website iMechanica is down right now, but I should find another way to sort of host this journal club. We were able to sort of publish kind of like a blog post on this idea, and we got some really interesting comments from other people in the community, basically talking about this sort of broad idea and why it can be challenging to disseminate or define benchmarks in the area of mechanics. And then we also maintain a very simple website where we basically list a bunch of data sets that we've sort of come across in our travels, sitting in on seminars, talking to people that have open access mechanics data. So this is data sets by us or Mechanical MNIST data sets, but then also others, including experimental data, for example, from a collaborator at UT Austin who studies heart tissue, or from our colleague here at BU who's running experiments where they have actually an autonomous lab 3D printing samples and crushing them and reporting data on that. So if this website is useful to you, or if you have ideas for things that you would like to contribute to it, please don't hesitate to get in touch, and we're happy to add to it because we're very excited to be able to sort of have conversations with people in the research community on these ideas. And if sort of you want more information on the work that I just discussed on surrogate modeling, or thinking about sort of this benchmark for phase field fracture, we have a paper on arXiv that has a lot more details in it. And again, I'm very happy to discuss with people further after the seminar. Okay, so that was kind of the first thing that I wanted to talk to all of you about, this idea of developing benchmark data sets. Now I'm going to kind of change topics a bit, and discuss this idea of performance metrics, with one example of the projects that we're working on. So we're working on a few different things right now, mostly in cardiac tissue engineering and wound healing. And what I'll show all of you today is kind of this snapshot, just focused on this one idea here. So this slide, it has sort of like all of the prettiest pictures that my lab generates. And this example right here shows basically a human-induced pluripotent stem cell-derived cardiomyocyte. So it's a single cell where individual sarcomeres are marked, and the red indicates contraction. This slide here shows a sort of digital image correlation S technique that we've used to apply to these movies of cardiac tissue. And this right here shows a snapshot of kind of a project that we're working on in wound healing. And really the overall sort of point that I want to get across is that we have a bunch of collaborators who are generating these very beautiful data sets. And what we can really contribute to that is figuring out how to turn those data sets into numbers or metrics or things that we can kind of meaningfully make comparisons from, and apply kind of quantitative rigor to some of this work, and build models for. So I talked a little bit at the opening of my talk about this project that we're working on with the Engineering Research Center in cardiac tissue engineering. And this has been really, really interesting work where we've gotten to learn a lot from experimental collaborators in cardiac tissue engineering. And like I was sort of saying in the previous slide, we've gotten sort of very focused on basically turning these kind of images and movies into quantitative information. So for the snapshot that I want to give you today, you don't have to understand sort of the full biology here, or kind of fully what's going on. But I just want to point out that these are going to be images of heart cells, these stem cell derived cardiomyocytes. And the way that we see these images, you have basically these Z-disc proteins that are labeled, and the individual units of sarcomeres connect these two kind of striations. And when you see those kind of move closer together, that's contraction. And if you see kind of a line of them, that's sort of like a line of sarcomeres that make up a myofibril, and that's what allows your heart cells to function and contract. Okay, so that's sort of the basic overview right there. And it can be very challenging to extract information from these iPSC-derived cardiomyocyte images, because these cells can actually be very, very kind of disorganized, and just really hard to sort of extract quantitative meaning from. And if you think about kind of a mature architecture of a heart cell, it's going to look a lot more like this. It's described as kind of this almost crystalline structure. You have these very kind of regular striations. And often when they're sort of trying to sort of mature these cells, they're trying to make them look more like these mature aligned cardiomyocytes, which is sort of a process to get to. But along the way, figuring out how to describe these more disorganized cells is a major challenge. Okay, so let's see. Let's have a sip of water. I've been talking too much. So there's kind of a large group of people who are working on analyzing this type of experimental data. And one really popular way that you see in the literature of analyzing these cells is using something called expert scores. And it is what it sounds like. The idea is basically they have people look at these cells, and they label them, say 1, 2, 3, or 5, ranging from less organized to more organized. But as you might imagine, if we're interested in kind of developing quantitative metrics, we're very motivated to develop something better. So you might be wondering kind of why is relying on expert scores as a metric problematic? There's a few different reasons. First of all, manual scoring images, excuse me, can be very time consuming. So this approach isn't necessarily going to scale to large data sets. And if you think about sort of this example shown on this slide, if you have 3,000 cells or 30,000 cells or even more than that, right? Like something that might be fine if you have a smaller data set will obviously break down. Critically also, manually scoring images leads to bias, right? Which can lead to compromised research outcomes. There are all sorts of documented forms of bias that you can get from this approach. Even just simply like if one person does the rating versus a different person, they might give different results and that can sort of lead to problematic outcomes. And then finally, I think another thing to think about is that, you know, if we're really trying to kind of do science here, manually scoring images doesn't necessarily offer more mechanistic insight, right? So what does it mean for a cell to be more organized? You know, what specifically are certain interventions actually doing in a way that kind of gets smeared out in these manual scores? And there are a bunch of different computational tools to analyze these cells. The work that we've been doing over the past few years is developing this tool called SMaRT graph, which performs segmentation tracking and analysis of the sarcomers in these beating cells. And we like this tool basically because graphs are kind of a useful mathematical approach to understanding and describing their behavior. And if we're tracking towards kind of building models of signaling in these cells, it lets us sort of set that up and do that in an interesting way. So we've been working on this software for a while. In 2023, my student Saeed completely rewrote it and made it more automated and had kind of better testing and checks there. And that's something that we're really proud of. And then sort of over the past couple of years, we've been really focused on some improvements that can build on having access to large data sets, like the one that's published by the Allen Institute that I shared a couple of slides ago. And sort of this kind of like, I don't want to go into too much detail because I want to get to the third part of my talk, but we've gotten very interested in basically thinking, you know, if we have kind of a bunch of different potential machine learning approaches that we could take to analyzing these data, what sort of meta methods can we put on top of that to do something like ensemble learning, to combine different types of segmentation to really improve our pipeline. And then we've also gone and tried to sort of show evidence of bias in expert scores and try to see if we can sort of push beyond that to do essentially potentially better work. So this slide here, just very briefly, shows what happens when we look at a large data set of these cells that are labeled by experts and try to basically extract quantitative features from these cells. We can do something really simple like perform principal component analysis with the features that we extract and see essentially that the sort of quantitative features aren't necessarily consistent across the way these things were scored by experts, and sort of have kind of quantitative evidence of this bias. We can also come up with some sort of specific alternatives to human expert scoring. We came up with an explainable clustering pipeline where we use machine learning approaches and just very simple kind of explainable clustering algorithms to provide sort of specific alternatives. And right now what we're doing is we're actually trying to work on developing a quantitative definition of what it means to kind of be kind of more organized for these IPS derived cardiomyocytes based on kind of this quantitative machine learning approach and feedback from our collaborators. So that's one thing that we're working on now. And I think that, you know, this topic might be a little bit far off from what some people who are doing scientific machine learning are working on. But I would imagine that because a lot of data comes in the form of images, a lot of you might be doing some form of kind of an image analysis along the way. And that's something we're very happy to talk about if people have sort of questions or commonalities in the future. And then also we have our software shared online if that's something that is useful to you at any point in your work. Okay, so I talked a little bit about our work in developing benchmark data sets. And then also in some of our work in defining performance metrics with our SMaRT graph software. I want to now sort of spend the rest of my time, maybe another like 10, 15 minutes or so, talking a little bit about some validation studies that we've performed using this kind of idea. Basically, there's all this kind of discussion right now, at least I see it, I feel all the time in the news, like, can LLMs do this? LLMs can kind of, save the world, whatever. Or LLMs are taking over the world in a scary way. It kind of depends on how you think about it. But so what we've gotten really interested in is basically, can we sort of look at this question in a somewhat more rigorous way, right? So we have this kind of general premise, right? How do we know when a method is effective, generalizable, and reproducible? We want to think about validation studies to kind of rigorously test these computational methods and reveal their capabilities and limitations. And we have this kind of big picture question, right? Can LLMs successfully write finite element analysis code? And really, like, why do we care about this question? Think teaching and education is one thing that definitely motivates me a lot, right? I want to understand basically where is the frontier of what LLMs can do? Are we teaching problems that LLMs can't solve? Can we tell students that LLMs can help them approach a certain class of problems? Like, where does all this fit in to the work that we're trying to do? Think about this a lot in the perspective of research, right? Can we trust LLM generated code in our research? Is there a future that we're looking towards where LLMs act as kind of computational engineers in our research frameworks? And then also just kind of very existentially, right? How do LLMs perform on a scientific computing test bed? Can we sort of conceptualize scientific computing as a formidable yet solvable challenge? And then, where is progress relative to this challenge? Can LLMs do my job, right? I think that's another thing that I think about a lot, right? Okay, so can LLMs successfully write finite element analysis code? How do we address this question in a systematic way? So what we've been working on is basically developing a benchmark to address this. So I think the first thing before jumping into details is I want to define a scope for the concept of sort of successfully write finite element analysis code. So this slide right here shows an example of basically a function and a test function, right? And I would say that I would be impressed if an LLM could, write a function that I specify, and then also write a test function, like a unit test for it. Um, because I think those things sort of in combination will nicely reflect a utility that kind of goes beyond just sort of an amorphously defined, like, solve this problem, right? So an example of what that might look like in the finite element analysis concept would be to say, define a task, quadrate shape functions and derivatives, that involves returning the value of shape functions and derivatives given natural coordinate points for an 8-noded quad. And for the test code, I would ask the LLM to implement the function so that output values exactly match some reference solution that I'm going to provide in my framework. And then for my test code, I might want to know, do the shape functions of this element satisfy the partition of unity? Do the shape functions of the element satisfy the Kronecker delta property? Anything else that I could think of that, would maybe be a reasonable thing to include in a finite element analysis software test suite. And then also push at some of the fundamental concepts that you might learn in like a finite element analysis class, because I'm also interested in thinking about how these things interface with that. So that's sort of the premise. And within this sort of FemBench framework, I want to think about the defining tasks, right? So each task is going to define the reference implementation and metadata for both code and test generation. So these are going to form the basis for evaluating LLM performance on well-defined FEM-related coding challenges. So a task is the basic kind of unit of an input. I created this is all on my GitHub, by the way, if you're curious and want to take a look. So I created a template for these task files where you have basically any dependency functions, a reference implementation, detailed doc strings that are going to get used in the prompt, test cases, known failures, and a bunch of metadata related to the task. So this is kind of what it looks like. And then what this sort of core FemBench software does is it ingests these tasks that are defined by the user and then converts those into prompts for code and tests. So this is what sort of a prompt might look like. I'm going to take you through it and 4 slides. So first of all, I had to implement a bunch of boilerplate text to get the LLM output to just be easily parsable. This was kind of annoying. It involved kind of going back and forth a bit, but you can see right, it says, you know, don't add any code outside the function definition, etc. It includes imports that are specified in the task file. And every aspect of putting this together is fully automated. Then it'll provide basically the code for any helper functions that you want to let the LLM use along the way. In this example, I don't have any helper functions. And then it'll basically define a function with a bunch of inputs. So here we have solve linear elastic frame 3D self-contained. And then it has a bunch of like specified, all with types, even though it's Python. I think this makes it kind of cleaner. Inputs, and then it has this very long doc string that's defined in the task file that basically says, specifically what this function is supposed to do. It includes details of the coordinate system, of what type of errors that it wants it to throw, so that the results are kind of, you can evaluate them essentially. Here's details on what all of the parameters should be, so very specific definitions here. Details on what the function is supposed to return, so return a specific NumPy array of the shape, right? In this case, it's asking for displacements and reaction forces. What type of errors should be raised, if any, and then any other notes that sort of make this kind of a deterministic, or what should be a deterministic request, essentially. And basically what happens is that we have these prompts defined, and then the ask is for the LLM to fill in the code for this function, right? So output should be this completed Python function, no extra text, explanations, or formats. And again, sort of this framework is set up in order to get the LLM output to be easily parsable, which is a little bit tricky and involves some back and forth. This is what an example of the test might look like for what the task prompt would look like for asking it to write tests. It's similar to the one we had before, but now it basically says, like, here are the test functions to implement, rather than asking it to implement the function itself. Okay, so we start with tasks. Our software converts those tasks into prompts. We have some LLM API calls. We have LLM generated code and tests. Then we ingest those in the software that we wrote, and we can put out some study results. And this is just sort of a look at what that might be. So the metrics that we're going to use are function correctness for the main code. So for the code that we ask the LLMs to write, it's just going to be a check mark if the LLM's outputs from the generated functions perfectly match the reference implementation for all sort of test cases or reference cases that we have specified in the task. And then for the test code, we're going to define error in terms of joint test success rate, which shows the percentage of LLM-generated test functions that both pass on the reference implementation and fail on all the known broken implementations. So in theory, this metric captures tests that successfully distinguish correct from incorrect solutions, but it's imperfect. It doesn't have like all potential expected failure cases included. It's just sort of a first pass. Okay. So here's what this actually looks like if we run this through a bunch of different tasks. So in this table right here, the rows are a bunch of different tasks that we asked these models to try. You can see they're kind of a range of different things. Some of them are very straightforward, like generate a linear uniform mesh in 1D. Some of them are a little bit more complicated, like elastic critical load analysis, things like that. And then we implemented a bunch of different models, GPT-4o, GPT-5, 2 versions of Gemini, 3 versions of Claude, and 2 versions of DeepSeek. And if you look at this row down here, you can see that like if you just do one run of these benchmarks with temperature set to 0, you get this performance where the best model, Gemini Pro, gets 19 out of 25 tasks, which I think is okay, but you know, it sort of shows we've identified a spot where LLMs can start to perform poorly. For the tests, the performance I think was a little bit worse. Same sort of table setup here where the tasks are rows and the different models are columns. And if we look at the sort of joint test success rate metric and look at averaged over all of the tasks, we can see that GPT-5 gets the test done according to this metric, right, 65% of the time. But most of the other models are not looking nearly as good. And even that, right, in finite element analysis or scientific computing, you want something to be correct 100% of the time. It doesn't seem good enough. But one thing that's kind of interesting, right, is that once we have this framework defined, we can start to tweak it and play around with it and see what happens if we do things like change the temperature. So sort of make the randomness and what the LLMs give to us increase a little bit. So we ran several runs with the temperature set to 0.25 rather than 0. And then we also experimented a little bit with using different system prompts. So system prompts just get added on to the basic task prompt that we have. Here we have one that says, you're an expert Python engineer in scientific computing, et cetera, et cetera. I think this is sort of like a joke that people tell online, right? What happens if you tell, you know, ChatGPT to do your homework while saying, you know, you're an expert at this class, like, does it help? Things like that. And we pushed a little bit farther with the second system prompt, where we said, you're an expert in finite element analysis and scientific computing. You completed your PhD under Tom Hughes and have spent over 10 years at Sandia National Laboratories working on computational mechanics problems. So we have, you know, these two system prompts, and we tried a couple of different temperatures, leading to basically 6 full runs through all the different large language models before we kind of decided we were spending too much money on this. For reference, it was like $150-ish total, so not too bad, but we didn't want to just keep running it for no reason. And this is basically the result that we get when we do this. When we think about kind of pass at 6, so if you run it 6 times, does it pass at least once as a potential metric to look at? And you can see basically from the slide, there are some tasks that every single model gets right at least once. There's sort of this intermediate region where it's, you know, sometimes, right, it's very hit or miss whether or not these models will get them correct. And then you also have this region kind of down here where they're basically always incorrect. And this region down here is basically asking the models to do you know, nonlinear finite element analysis tasks without substantial helper functions or guidance. And that's where things kind of tend to break down, and it's sort of maybe too hard or too outside the scope to perform well. And then I want to point out, right, that the prompt that we looked at was for solve linear elastic frame 3D self-contained. I think this is like a standard, maybe like homework assignment or project, and, you know, a master's or first year grad level finite element analysis class. And you can see, just for reference, right, models get this right some of the time, but without an oracle, it would be very difficult to know or trust these results. And I think this kind of gives me maybe like the best intuition for how these models are doing right now overall on these types of problems. And you know, this is very much ongoing work. We have results and all of the code on this GitHub repository that I'm sharing here. But yeah, just overall, relatively few tasks that all models get correct all the time. Test code performance, both at the pass at 6 and on that first deterministic run, is a little bit worse than main code performance, which I thought was interesting. Maybe that's just a less popular thing to have in the training data. And then if you actually look sort of at the code that the LLMs are spitting out, there's kind of 2 types of error that I'm seeing. The first one is an example where kind of all models are failing on a task. It's just kind of too hard. And then the second one I think is a little bit more interesting, where a pattern that we often see in this LLM generated code is that some mistakes are kind of like due to almost like a switch in notation partway through solving the problem. It's almost like this notation mashup error where it's kind of putting together information from multiple sources. But this is very much a work in progress. And yeah, if you want to see kind of all of the specific examples and code and tasks, definitely take a look at this GitHub repo. And so that is sort of more or less what I wanted to talk about with all of you today, taking you through kind of this kind of like high level motivation, and then thinking about benchmark data sets, performance metrics, and validation studies. And yeah, that's pretty much it. Thank you all very much for listening, and I look forward to questions.
Thank you. Thank you, Emma. As always, wonderful. I do have a couple of questions, but maybe I'll hold it back. I know your work very well, so I'll open the floor for the audience for questions. Shobik, you want to go first?
I can. I can.
Okay.
So yeah, I mean, excellent. The first part is, I mean, really useful to us, I would say, that because my group works on developing algorithms, so we can definitely use those benchmarks. But I think there is a question in the chat box. Maybe I will ask and then we'll go there.
Oh.
So the last part, right? This is I know understand is a ongoing work. So what you're trying to do is that you are trying to test whether LLM can write finite element codes, right?
Yeah, just seeing whether or not it's possible.
Right. So now there is a parallel line of work, almost same. For example, let's say the make agent work from MIT, which actually tests LLM whether it can write a Phoenix code, because Phoenix has the finite element actual implementations within it. So now you just need to write the script, because let's say weak form and implement the correct boundary, the correct material. And they claimed it kind of works for, I think, plasticity and elasticity, if I'm not wrong. I saw it. So did you check those? And I mean, I understand yours is more rigorous, like it's like a LLM taking a FEM class where you will do everything by step, right? Forming the assembly matrix, local stiffness, global stiffness, and all of those things. But yeah, what is your opinion on this to work for practical use, let's say, because we have the practical tools, right?
Yeah,
The
totally.
Phoenix
I
and
mean,
those.
I think the thing that like so I think that the question of whether or not LLMs can write finite element analysis code from scratch, I think, is a bit academic, although it of course builds to this bigger question of, could say like an LLM implements a new function to contribute to a Phoenix code base. And I would say like if it can't do the simple stuff, it probably can't say contribute to the Phoenix code base. And maybe like this line of work is ultimately tracking towards that application. When it comes to writing code in Phoenix, I love that question because a student in my group is Irfan, is currently working on trying to develop basically like a Phoenix agent that definitely my group does everything in Phoenix we would love to use, and if successful we would publish it for others to use as well. And we're definitely having trouble. Some of the problems are because a lot of the Phoenix documentation is a little bit sketchy. There are errors in the Phoenix documentation that then get reflected if you do something like a RAG to define your agent. So we're trying to manage that. But I think it's an area where, like, from a practical perspective, having an LLM that can write Phoenix is probably a lot more useful than an LLM that can do sort of your grad class homework. So I think it's sort of a direction that we're going in. But at least in our experience, we also don't think they're quite there yet.
Yeah. I also believe so. And I'm guessing that you have not tried fine tuning yet, right? I mean, these are all off the shelf models without any fine tuning, let's say, on some Phoenix codes
all
or
off-the-shelf models.
some.
Yeah, and part of the thought behind that is basically like, I think fine tuning can be great. It can do great things, but I would guess that, like, say that you have ChatGPT 4.0 and you fine tune it, probably ChatGPT 5 is gonna do better than your fine tuned previous model. So I think some of my mentality is that I would kind of rather be ready to assess the next thing that comes off the shelf. But that's just my personal preference. And the benchmark should work for models that are fine-tuned as well.
Yeah, agreed. The only thing is that I mean, ChatGPT 5 they might not have. I mean, it is very easy to get deep learning codes, not so easy to get FE codes online. So what
Yeah.
data it is trained on is, I think, the main bottleneck, right?
Yeah, definitely. Yeah,
Yeah.
if there are any LLMs fine-tuned on FEA data that you could point me towards, it would be great to run them through these benchmarks
I
and
don't
see
think
if
there
it's
is any.
better.
I don't think there is any. But I thought that yeah, that might be a good direction. I don't think there is anything that is fine-tuned. Because to generate those data set with FE is itself a big challenge. Maybe something
Yes.
Mhm.
in the direction you are pursuing, right, of generating benchmark data. So I think that will be a great benchmark data.
Yeah, it would be
Yeah,
really cool. Yeah.
yeah. Yeah, so
Um,
that's all from my side. But I think in
I
the
think there
chat there are
is,
some questions. Yeah,
yeah, yeah.
Sumata, go ahead.
Mohammed Saki, if you're online, you can actually ask your question.
Yeah, hi. Thank you.
Hi.
So, like the talk was quite insightful. So, like since I am Mohammad Zaki. I'm a postdoc here at Hopkins with Professor Michael Shields. My experience has been in the development of large language models for materials domain and evaluating their capabilities on code writing tasks for materials in chemistry, just like you have done for finite elements. So, like my some of my insights that I thought that I would like to see here are that instead of like in addition to evaluating the accuracy of the models, like how many questions did they got right, we also like to report that what are the kind of mistakes that it made on the 6 questions that you showed, that where it was not able to, like none of the models were able to answer that
Mhm.
kind of thing. So people have like classified those mistakes into conceptual and the like when we were solving numerical problems, like the conceptual problem and the numerical error, so which is also similar to in the finite element when we like do these kind of things. So if that insight could be gained from those errors, that will like really inform what next steps should be taken to improve those capabilities.
Mhm.
And yeah, and my next question was like, did you try chain of thought prompting, or you just like did that system prompt and then evaluated all the codes?
Chain of thought prompting, as in like including in the prompt,
Yeah,
like a think about this question for a long time.
yeah.
I did not in any rigorous way. My intuition is that it probably wouldn't help that much in this context, just based on kind of playing around with it a little bit. But yeah, that's something that is maybe on the list of things to include.
And another thing that can also be included is that the models that like that were there in the benchmark. So there are some code specific models like that are trained solely for the purpose of generating the code. So if that they can also be tested, that I think that will be like much better. And did you also allow in the prompt that LLMs can use any external libraries or just like native Python code only?
So they're allowed to use external libraries specified. So it's allowed to use like NumPy, SciPy, stuff like that. We didn't have it using Phoenix, because that just wasn't the scope, or OpenSea's Pi or anything like that. But I think sort of looking ahead at your question on like LLM-based agentic workflows, and the previous question I was just talking about with Suvik. I think that is something that is really interesting to look at and is perhaps maybe just a little separate from what I was presenting.
Yeah. So what I have experienced in the agentic domain is that once you like give your entire GitHub repository to that agent, it will like keep on iterating, or it will keep like try to write the test case itself um for the code that you have asked it to write, and then it will try to validate whether that those test cases are passing or not, and then like they also generate a report towards the end that okay, these are the questions on which it failed, these are the mistakes that it made, and so that so it can be done easily using proprietary agents, but making
Mhm.
an agent specifically for this work, that's a quite a challenging task.
Yeah, yeah. Yeah, and I think it's always a question, right? Like, are we trying to benchmark these proprietary tools? Are we trying to develop everything from scratch? What is
Yeah.
the ultimate objective? And I think like you know, in putting together this initial benchmark, I think that like my biggest motivation for it was basically like, you know, next time I teach a finite element analysis class, I want to be able to just hit run and say like, oh, can the latest models solve all my homework problems, right? And I think that like, you know, getting at these like bigger questions of, you know, can we trust LLMs to use Phoenix or Abacus or any of these tools, I think is super exciting and yeah, definitely like something to be thinking about next.
I also encountered this similar phenomena that you mentioned about teaching an FEM class. So when I was at IIT Delhi, I specifically asked students to write Python codes for solving different finite element assignments. So, but what I took care is that all the solutions for those questions were already available in MATLAB. So if some student could find that, I also like gave that book into the class. Okay, this is the book that you can refer to. So some students were intelligent, they could just translate the MATLAB codes into Python codes, but like some of them were not able to. So it's like yeah, it's a good thing that whatever assignments we are giving, can students use on any existing tool to just, you know, solve that. Or
Mhm.
maybe we could design harder assignments for students.
Yeah, I think there's also this like interesting question, right? Like, it is it are these models not doing so well on these tasks because of lack of training data, or is it because like, you know, there's something kind of fundamental where like even if they have a ton of different training data, the discrepancies in notation are insurmountable for the way these current models are set up. And yeah, it's something I want to learn more about and new area for me. So yeah, thanks for your questions.
Are there more questions from the audience?
There is one more in the chat, I think, Kunal. So can we fine tune existing VLMs, video language models, to model multi-scale biomechanical deformations in mechanical MNIST, or do the physical constraints or of biological tissue require specialized foundation models? So can it be
Uh,
done based on videos? I think that's the question.
yeah, so what's
Mm.
what are VLMs?
Video language model. So you take the video, it's a language, you take a video of that deformation pattern and can it learn from there?
Okay. I think
Oh,
let's
they
see,
have
vision.
vision language models.
Yeah.
Okay. Can we fine tune existing vision language models to multi-scale biomechanics? Um, my intuition is that they probably require some more specialized foundation models. You know, I have a colleague at BU, Keith Brown, the one who does the high throughput experiments with the 3D printed materials. And he's kind of like, isn't COMSOL like a foundation model for mechanics, something like that?
Yeah.
It's like it's like an interesting way of thinking about things, right? But then when you're dealing with biological tissue or say like, you know, an experiment on biological tissue, there are all these questions, right? Like what are your boundary conditions? How do you sort of handle things like that? And I think that basically I think that in addition to kind of like maybe like fine tuning or sort of pushing foundation models from other fields or leveraging them to be relevant to mechanics and multi-scale biomechanics. There are also a lot of differences in the type of questions that we would aspirationally answer with these machine learning approaches. And I think it's very sort of like application specific. Yeah, kind of a non-answer, but I think
Yeah.
there's a lot of open questions.
Yeah. I also think, to just to add to what you said, I also agree that I think vision language VLMs will not work because there will be some parameters which you cannot infer from an image.
Mhm,
Let's say the mechanical MNIS, right? Two materials
mhm,
soft and stiff, but let's take two scenarios, exact same configuration. But the stiff material has a different elastic modulus in the two cases. I
mhm,
mean, you cannot probably infer it from a single frame,
mhm.
maybe.
Yeah.
But yeah.
Yeah.
Yes,
There is
Sundata, you
a
have questions. Right.
yeah. So I think there is a line of work which Krishna from UT Austin is doing. He's trying to infer the material properties from videos.
Mhm.
And I think it is his project on Land Rover on the moon.
Oh, Krishna Kumar or
Krishna Kumar, yeah, from
yeah.
UT Austin. I remember. We do have a neural operator journal club with him. So we saw a presentation from one of his students. So that's one. Emma, I wanted to ask you: have you seen Professor Krishna Garikipati's work on the creating an agent for the FEM class?
Yeah, I have. It's really cool.
Yeah,
Yeah. Yeah, so I guess for people who haven't seen it, they're able to leverage like their Coursera course, basically the data from their
yeah,
Coursera course,
yeah,
to fine tune, right, a large language model to be like a course tutor, right? That was super
yeah,
cool.
yeah. On a very similar line, even my group has actually developed a TA agent for classes which are big. So I'll share it with you. We haven't like
Yeah, awesome.
submitted the paper. I'll share it with you.
Yeah, which class?
Statics and mechanics. We have like
Oh, no
90
way.
students.
Super cool.
So
Yeah,
we
that's
have like
awesome.
12 TAs and we want to just relieve the TAs from the
A
TA
little
job.
bit, yeah. Yeah, what so the agent is like a kind of like chatbot with like a RAG type thing
Yeah,
or
it is a
oh,
RAG
super
output.
cool. That's
I'll
awesome.
share it with you. Yeah.
Yeah, nice.
I have a couple of questions on the face field data, but I'll reach out to you separately. Uh, it's okay. We are already over time.
Yeah, I mean,
Yeah,
I was
yeah.
also interested in the like the dimension and all those things, but I will to reach out
Yeah,
separately.
yeah,
Yeah,
yeah.
yeah. Happy to chat in the future.
So thank you so
So,
much, Emma, for
Yeah, thank you both.
accepting our invitation and also for giving this wonderful presentation.
Yeah, thank you all for listening. So, yeah.
thank you.
Thank you. See you.
Yeah. Yeah, cheers.
Bye.
Bye.